At the end of 2018, he joined the S-Phoenix experiment. That's an upgraded experiment of the BNL RHIC, which is expected to start operating next year, 2023. And his team and the collaborators in National Taiwan University here have contributed to the construction of the S-Phoenix INTT detector. And in 2019, he initiated the myography project. That's an interdisciplinary study between the particle physicist and the geoscientist at the National Central University. The team designed and constructed the muon detector using the scintillator and the SIPM technology. The project aims to use the cosmic muons to study a few geophysical issues in Taiwan. So today he's going to tell us about his journey for the hunting of rare Higgs decays. So let's welcome Professor Guo.
Okay, so many thanks for the invitation from Professor Wu and also Chairman Zhang. This is my first colloquium to the NTU joiner colloquium. And okay, so it's really a great pleasure that today I'm going to talk about the search for the rare decay and CMS, and I have been working on this search for 10 years. And then I will also talk about my recent experiment in Taiwan. There is a Myongua project at NCU. So actually, okay, go to the next page. Okay, and so actually the result I'm going to present will come from two CMS experiments. The first one will come from a compact muon solenoid, and this is experiment LC. And the second one will come from my Myongua project, and my student named it as a CMS experiment as well. So they call it the cosmic muon scanner. Okay. Okay. So then I will start from a very from a short introduction about the particle physics. So what kind of questions we would like to address in particle physics? Actually, we try to address two simple questions. The first one is what are the fundamental elements of matter, and what are the interactions between these fundamental elements. And so to me, working on the experimental particle physics is just like a journey into the heart of a matter. And so what I show here, and this is the number of the fundamental particles we know at a given time, and as a function, as a time that as our knowledge improve. So actually, in the ancient Greece, told us that our universe was made of earth, air, fire, and water. And later, we know actually there are more and more fundamental elements to construct our universe. And then just about before the 1895, actually our knowledge is like this. So this was the elementary element we knew at that time, and then those elements form this nice periodic table. However, in 1895, J.J. Thomson discovered electron, and later Rutherford and other physicists discovered the proton. So suddenly that the number of fundamental particles to form our the matter actually decreased from about 100 immediately down to about 2. Okay. However, this number keep increasing as we discover more fundamental particles at that time, like neutrons or other particles like kaons or pions at that time. However, later, around the 1960s, actually the Gell-Mann proposed the quark model and say actually some of the particle we call it hadron, we know actually they are formed by 2 quarks over 3 quarks. Okay, and then later in 1974, 17 discovered the fourth quark because Gell-Mann only proposed 3, and however the 17 discovered the fourth one, and later we find more and more fundamental particles. Okay, so this is the knowledge of the fundamental particles we know before we turn on LHC. Unfortunately, this is still the one we know today. And so here we know that we have 6 quarks, and then we have 6 leptons, and 3 are charges, they are neutrinos, and then we have electrons. Well, we know electron very well, and then we have the muons, and the muon is going to be the key role that's in my second part of my talk. And then we have tau, and then we have this gauge bosons to mediate the force between the particles. Okay, so these are the elementary particles we know so far. And so in order to look for more fundamental particles or new interactions or any new physics we don't know yet. And then so of course we need a powerful machine, and we need to increase the energy, right? Because sometimes you hear that we call the particle physics, well, actually there is a branch in particle physics we call high energy physics. And the reason why it's high energy because like what Einstein told us, that E equal to mc squared. And we need to increase the energy so that we can discover the heavier particles we haven't found in our life. So in this LHC that we operate the proton-proton collisions at 14 TeV. And actually, this 14 TeV is not really a large amount of energy because if you are talking about 1 TeV, actually this is roughly about the kinetic energy of a flying mosquito. So actually what makes LHC unique is that we try to squeeze this energy into a space that's much, much smaller than the size of a mosquito. Okay, so that's the difficult part. And then LHC that we collide the proton bunches per every 25 nanoseconds. Okay, so the rate is quite high. It's 40 megahertz. And then the total cost of collider is about 3.7 billion Swiss francs. So actually, this is not quite a lot of money. It's just about one recent British aircraft carrier. So if we do not need to go for the war, maybe we can build more colliders. And then, yeah. And so of course, we try to build this kind of powerful machine. And of course, we need to have some important physical to look for. And one of the physical, and I think this is actually the most important one we would like to explore at LHC, is that actually, if you look at the table I showed you earlier, and if you look at the mass of each fundamental particles, then you will find actually some particles quite heavy, like a top quark, and some particles quite light, like electron, or some particles are massless, like photon or the gluon. Okay, and so this has been a puzzle. That's why some particles are heavier and some particles are lighter or even massless. And so the Higgs mechanism was proposed in 1964 in order to explain the origin of mass for these fundamental particles we know. Okay, and so in order to prove this Higgs mechanism, actually in this Higgs mechanism, a Higgs field was proposed. And in order to prove the existence of this Higgs field, and then we need to discover a particle called the Higgs boson. Okay, and of course, the Higgs physics is not the only one physics program that we have at the LHC. Of course, when I joined CMS in 2002, At that time, there was a nice plot and show people that well, if we turn on HC, after 1 month we can discover this, after 3 months we can discover this, and after 1 year we can discover that. So actually, we have quite rich for physics program LHC. Like we can look for the supersymmetry, and we can try to understand the matter and antimatter asymmetry. We can look for dark matter and look for multi-dimension and look for more fundamental particles. Okay, and so by the end of 2000, sorry, this is as of last week. So CMS already published and submit about the 1100 papers. So actually in CMS, we publish a paper in every 4 days. Okay, so yeah, so actually a lot of result has been squeezed out from our data. Okay, and then this is how the CMS detector look like. So this is a giant machine. Well, but comparing to another one, that's Atlas, actually it's not that large. However, it's quite heavy because we use the return yoke and we also use a lattice state as our calorimeter, and so it's quite heavy. And so the diameter is about 15 meter, length is about 21.5 meter, and we use a strong magnetic field for Tesla. And why do we need a strong magnetic field? Okay, so this is show you an event display for one proton collision, and a lot of particle will be produced. And actually, if you don't have the magnetic field, so all the particles will go straight. And then, so if we turn on our magnetic field, you can see the low momentum particles will bend. However, the high momentum particles, we are usually interested in the high momentum particles. Then you can see actually those particles will not bend. Actually, they bend a bit, but you cannot really see it by eyes. You really need to use a computer and program to analyze it, and then you can really find out its momentum. Okay, so once you turn on this strong magnetic field, and those high momentum particles will stand out, and then we can, of course, we can apply some selection criteria, and then we can find those particles we are interested, and then we use them to discover the physics we want to look for. Okay, and however, that working on the particle physics is quite different because when I was an undergraduate, actually I work on the condensed matter experiment. And actually, we usually have a sample and we just perform one measurement and then we can publish the result. And it's quite easy. Wow, okay, I shouldn't say that, but okay. Anyway, what I mean is that you do not need to repeat experiment many times, okay? However, in experimental particle physics is quite different, is that we need to accumulate statistics. So we need to have a lot of collisions, and you will see this in a few minutes. So this is a quite basic formula when a student start with the experimental particle physics, and then this equation you need to know. So this simple equation is n equal to cross-section times the luminosity. So when collision energy is determined, then actually the cross-section is determined. Okay, this cannot be changed unless you increase or decrease your collision energy. Okay, so this is a fixed number for a given collision energy. And however, we would like to look for some our signal, right? However, usually the signal we look for is rare. It cannot be produced easily, okay? Or they will cannot be produced quite often. So therefore, that in this formula, the n, so n represents the number of signal events for a given physics process we want to look for. And so in order to increase the number of signals that we can detect in our experiment, then once the cross-section is fixed, then we need to increase the luminosity. So the luminosity here means that the amount of data we have. Okay, so we need to increase this luminosity. And actually now let's see that the chance of creating and finding a Higgs boson at the LHC. So let's assume that it's about 3,500 grams of rice in a bowl. Okay, and so if we really want to find a Higgs boson, namely 1 gram, so it's like finding the Higgs in HC is like finding 1 gram in a bowl of rice eaten by everyone in Taiwan in 1,000 days. Okay, so you can go back to calculate how many collisions we need. So we really need a lot of collisions. So namely, we really need to have a lot of luminosity, namely amount of data on the disk for us to analyze and then look for the Higgs boson we want to look for. Okay, so this is the amount of data we collected between 2010 and 2018. So here you can see that for each data taking year, actually the luminosity kept increasing, and this is very nice. However, as we often say in Mandarin, that 有一好就没两好. Okay, so it's very nice that the luminosity increase. When we increase the luminosity, well, there are a few simple factors. For example, you need to increase the number of proton bunches in the collider, and you need to squeeze the proton size, and you need to increase the squeeze the proton bunch size, and then increase the number of protons within a proton bunch. Once you do that, you increase the luminosity. However, at the same time, you increase the number of proton-proton collisions in a given proton bunch collision. So in this complicated pattern I show you here, this is the event display for a given proton bunch collision. So in this particular proton bunch collision, actually we have 50 proton-proton collisions at the same time in our detector. So therefore, in order to find out the real signal we want to look for, is rather complicated from this complicated pattern. So for example, if we want to look for 2 photons, okay, and we want to use these 2 photons to reconstruct the invariant mass, and then the formula is what I show you in the bottom of the slide. And what's important is that, of course, you want to measure the energy, right? And at the same time, you also want to measure the opening angle between these 2 photons precisely, right? This is theta gamma gamma. If you measure this theta gamma gamma wrong, then you will not be able to have the right diphoton invariant mass. So therefore, in order to find out the right opening angle of these 2 photons out of these 50 proton-proton collisions, and this is quite challenging, that you need to develop a dedicated algorithm in order to find out the right vertex. Okay, so actually in the LHC round 2, that here you can see, for example, in the 2015, in one bunch proton collision, actually the average pi up here with the number of proton-proton collisions in our language, we call it pi up. So the average pi up is about 13, but in 2018, this number was increased to 37. Okay, so it's quite a lot. It's quite difficult to deal with. And to be honest, in 2029, this number of pi up will be increased to 140 to 200. So it's going to be very challenging when we analyze the data. And another thing is that when we increase the luminosity, so actually this means that you increase the radiation damage to your detector. Okay, so for example, in CMS, that our electromagnetic calorimeter employs about 76,000 late-time state crystals. Okay, so before we have the collision, actually they are quite transparent, as you can see in the photo. I believe nowadays, if we open our calorimeter, in particular in our NCAP region, they are not transparent anymore, because as you can see from this plot. And this plot show you that actually we have a laser system, and we can inject a laser to our crystal, and then we can measure the expected light year in the end of the crystal. So therefore, originally expect if you inject, like let's say, well, make an example. If you inject 10 photons, then you expect to collect 10 photons at the end of the crystal. Okay, and so here we can measure the relative response to the laser light here. So you can see here, well, this eta means that smaller eta means that it's middle of our detector, And then for the higher eta means that you go to the forward part, namely the end cap region of our detector. So you can see actually in the small eta, actually you can see the radiation damage is not high because the response is still very close to 1. However, here you can see that when you go to high and high eta, means that you move from the center to the forward region of a detector, actually you can see a response decrease. Okay, so that means that right now, for example, you can see in our very forward region, the relative response is below 20% already. Right, so I believe the crystal are not transparent there. It should be dark now there. Okay, and then this is one thing. So therefore, you need to calibrate this 76,000 crystals carefully. And another cumbersome thing is that if you look at this pattern, if we want to develop a simple formula, and even if you want to make a prediction and how to make a projection in order to calibrate your detector well, if you look at this pattern, it's impossible because you can see that sometimes that response will come back because we have a shutdown in the machine that we don't have the collisions. Then the response will come back, but then decrease again when we have the collision, and it will come back again. So it's impossible to predict, and so therefore you really need to calibrate your data, your detector from the real data. Okay, so this makes our life quite difficult as an experimentalist. And another thing is that this is the pre-shot detector that both of NTU and the NCU involved in the construction and commissioning. And so this detector on chip sensors, and you can see the response in our silicon sensor and measured from 2015 to 2018. And you can also see actually that this detector also suffer from the radiation damage in the different regions. Okay. And okay, and now once we collect the data, and of course we need we would like to find out the physics we want to look for. And so one of the important physics parameter we would like to measure is the mass. And so as you learn from in the general physics course, that m actually is equal to square root of e squared minus p squared. And so in this let's assume, actually, we perform the measurement in 3-dimensional, but let's assume in one direction, there is no, well, the momentum component can be ignored. And so if we only look at the 2-dimensional phase space, and then from this 2-dimensional phase space, we measure the momentum. So we measure its projection on the x and the y direction, and you can calculate this p square, and you also measure the energy, then you get an E square, and then you just put these two particles together, and then you can measure the inverse mass of these two particles. Okay, so in the end, for example, if you want to look for a new physics, let's say a new particle, that it would decay into a pair of muons. Okay, so in our detector, we just select two muons, and we use the formula in the previous slide, and then we compute its inverse mass, and then we make a plot like this. So in this mass spectrum, then you can see for most of the time it's a falling spectrum. Okay, but sometimes you have some resonance, and that indicates the existence of a particle there. So in this photo, that it shows you that these are all the particles we have known so far. And of course, that we quite often, not always, but quite often. So what we do is that we rely on this kind of mass spectrum. We have a falling spectrum, and then on the falling spectrum, we want to look for a bump that haven't been observed in the previous experiment. Okay, so let's go back to about 10 years ago. So at the beginning of 2012, and both of Atlas and CMS submitted two papers to Physics Letter B. Okay, so the CMS one is on the histogamma gamma, And here you can see this is the data from CMS at that time with very small amount of data at the 70 eV. And on the right, this is the Atlas result on the His2GG24 lepton with the same amount of data. Okay, and here I put the last sentence from the abstract from each paper. So the CMS conclude that well, it seems that there is a small bump around 125 GeV, but CMS conclude that we need more data and to make sure that the origin of this XX. And in the Atlas one, they claim that there seems to be some bump around 125 and 244 GeV. However, we perform careful statistical analysis, and then so none of these assets are significant. Okay, so this was a conclusion in the beginning of 2012. However, on the July 4th of 2012, that I think many of you already know that actually in this animation that you can see that once we start to increase the statistics, actually we gradually to see a bump or a peak we have never observed around 125 GeV. And so here you can see is the result from the both of CMS and Atlas. And so both experiments show that a very significant bump, really around the 125 GeV. So both experiments claim the discovery of the Higgs boson at that time. So actually, it took us 47 years, 8 months, and 15 days to discover this particle. Okay, after it was proposed. So it has been 10 years after we discovered this particle. And so what we know about this particle, okay? So we know that in standard model, the Higgs boson can be produced through a few potassium mole. The first one that we call it the Guang-Guang fusion. And then the third one, the second one is we call it the beta boson fusion. So in this beta boson fusion, that the Higgs can be produced together with a pair of quark, okay? And then we can also have the associated potassium, like when the Higgs boson is produced, and then the W or G boson can be produced together. And then we can also have the potassium called the TTH, that namely that when Higgs is produced, then you can have a pair of top quarks. And so the last one is quite interesting, although it's quite small, and because this can allow us to probe the direct coupling between the top quark and the Higgs boson. And so far at the LHC, we already discovered all the major potassium modes. Okay, and on the other hand, the Higgs boson can decay, okay, and into a different final state. And so far, the 5 major decay modes have been observed, and we also have the evidence for a rare decay, like Higgs get into a pair of a muon. Okay, this is what we know so far. And how about Higgs mass? Higgs mass actually is a free parameter in the standard model, so that's why it took us so long to discover this Higgs boson. I mean, if we know the Higgs mass in the beginning, we already discovered it a long time ago. And so far, in CMS, for example, we use 2 decay mode with a very good mass resolution, the Higgs 2 gamma gamma and the Higgs 2 GG24 leptons, and then we measure the Higgs mass. So here you can see that right now the best mass measurement of CMS is that the mass of this Higgs boson is at 125.38 GeV, and the precision is about 0.12%. Okay, so this is the best Higgs mass measurement of CMS so far. And then how about the Higgs coupling strength with standard model particles? So here in CMS, we also measure the coupling strength for these 6 standard model particles from the top and then to the G and to the W and then to the B quarks and then tau and also muon. So here you can see so far actually the results actually is still consistent with the standard model prediction, and the precision of this coupling strength is at about 10 to 20%. Okay, and so we hope that by adding more data and also the improvement of the analysis technique, and then we hope that we can continue reducing this to improve this precision, because this precision is quite important for us to say whether the Higgs boson we discover whether it agree with the standard model or not. Okay, and of course, the discovery of the Higgs boson is not the end of our physics program. Actually, instead, I mean, this discovery actually give us a new opportunity to look for the new physics. So for example, we can try to look for the Higgs decay to a long-lived particles, and we have done this in both of CMS Atlas, but unfortunately so far we haven't discovered any new physics so far. And in addition, that actually when LHC enter the high luminosity era, and the measurement of the dihiggs production is quite important. And so actually right now, even with in the round two with the data we have so far in CMS, we already start to build up the analysis technique and the strategies, and to look for the production of the dihiggs and to look for the new physics at the same time. Okay, and so here I will switch to the main topic of my talk. So here that I would like to talk about the rare Higgs decay in the dilepton and a photon final state. And actually here you can see this is the Higgs, and then will decay to the diphoton and the photon. However, if you compute the dilepton emergent mass, and actually its mass spectrum is going to look like this. This is similar to what you have seen in the previous slide. And so this is we have a Falling spectrum, and on top of this Falling spectrum, we have a few resonance we have known. Okay, so in this search, actually there are three interesting final state that my group has been working on. The first one is a Higgs 2G gamma. So the Higgs will decay into a G boson, and the G boson will peak around 91.18 GeV, and then with a gamma. And then at the same time, actually, usually when people look at the Higgs 2G gamma, they only start at the mass above 50 GeV. However, actually, in this final state, actually, the dilepton emergent mass is a Falling spectrum. So actually, you should not just limit yourself to the phase space above 50 GeV. So that's why we propose to also work on the mass region below 50 GeV. However, below 50 GeV, actually, the majority is the Falling spectrum. So this Falling spectrum actually is the Higgs to gamma star gamma, but this gamma star doesn't peak. It's a Falling spectrum. So we call this is a non-resonance search. Okay, so it's a Falling spectrum. And actually, this one is the gamma star is quite interesting, because if you look at the branching ratio of the Higgs 2G gamma, and usually we look at the decay of dimuon plus photon or dielectron plus photon, they have similar branching ratio. But with this gamma star, actually you can see the branching ratio actually is quite interesting. The electron has a larger branching ratio comparing to the muon, and this is because this gamma star mass is quite small. So that's an interesting part. And then at the same time, you can also look for a couple of resonance like Higgs to Zi gamma or Higgs to Epsilon gamma. However, I don't have too much time today, so I will just focus on this Higgs 2G gamma. Okay. So in this Higgs 2G gamma, actually these are the Feynman diagram, and they give us this Higgs 2G gamma to L gamma. And so you can see these diagrams, actually they are loop-induced decay. So they are sensitive to the physics beyond standard model. So the signature is that we look for an opposite sign isolated electron pair and an isolated photon. So this gives us a clean final state with good mass resolution. And so we set a threshold on the diaphoton emitting mass at 50 GeV. So this is used to separate Higgs to G gamma search and Higgs to gamma star gamma search. And more interestingly is that in the standard model, actually the branching ratio of this Higgs to G gamma to the gamma Higgs to gamma gamma, actually in standard model, this number is fixed. So this number is 2.27%. Okay. So this is important. Then yeah, we will come to this later. Okay, so this is how the Higgs to G gamma will look like in our detector. So this is an event topology. So we look for example, in this event, we look for two muons shown in red, and then we look for a very small energy party in our electromagnetic calorimeter. There is a photon. The difficulty of this analysis is that actually we deal with very low PT photons because we have a G, and his mass is 125, and then the G mass is 91 GeV, right? So therefore the photon PT is going to be very low. So this make it difficult to this analysis. Okay, and before I go on to show you the result, actually there are a few important factors in this kind of searches. The one thing is the luminosity, namely the amount of data. So if we discover a peak, then we will try to compute the significance. Okay, and so if we have 3 sigma, we say we have evidence, and then if we have 5 sigma, then we claim we made a discovery. However, if we don't find any interesting signal, then we usually set a limit on the signal strength. Okay, and so in this, you can just don't improve the analysis technique, and then you can just wait for more and more data to come. So if we have more data, then you can see the significance actually will increase, and then the limit, namely the search sensitivity, actually it will decrease. Okay, and then of course, as an experimentalist, we should try our best to improve our analysis technique and also strategy. Okay, so within a given amount of data, then we can make a better sensitivity. So that's all one we want to do. So there are 3 things you can do. So one thing is that, of course, you can try to make your signal selection efficiency higher. So here you can see that, I make it object in the top row, sorry. So you can see that if we increase the number of signal, actually the significance will increase, and then the limit actually it will decrease. Okay, that's all we want. We want the significance to increase if we have signal. We want the limit to go down if we have if we don't have signal. And then another thing is that we want to control our background better. So here you can see is that if we can reduce our background, then actually the background, you will get better significance. Okay, and then the result is going to be better. And another thing is that the resolution. So the mass resolution is quite important in our search. Is that if you have a very good resolution, like what I show here, like 1 GeV, actually you can see the significance is good comparing to the resolution of 5 GeV. And you can also, in the bottom part, you can also see actually the limit on the signal strength with 1 GeV is smaller than the resolution of 5 GeV, right? So that's why in our analysis, we always want to keep our signal efficiency high. We want to keep our background efficiency low, and then we want to improve the mass resolution. Okay. And then in the next few slides, I will show you a few this kind of plot, like we call it limit plot. And here I will talk about how to read this limits a bit. So actually the y-axis, this is the Higgs production cross-section with Q divided by the expected Higgs cross-section in the standard model. So that's y-axis. And as I mentioned that in the beginning, actually we didn't know where the Higgs boson is. Okay, so that usually we will make this plot as a function of his mass. Okay, and then so what's interesting is that we want actually if you have okay, what usually we look at this expected limit. That is expected without Higgs. That's a background only hypothesis. And we want this, first of all, we want this, the dashed line to be closer to 1. Okay, if it's close to 1, namely we say we have a sensitivity to standard model. And if we go below 1, it's also good because we say, oh, we start have the power to exclude this new physics. And then another thing is that once your expected limit approach 1, then another thing is that we would like to look at observed limit, namely the solid line here. And this means that the result from our data, okay? And so if you have this expected limit at close to 1, and if this solid line about 5, it's about 1, then we claim that there is excess there, and maybe we have a we find something new there. Okay, so usually it's the way how we look at this limit plot. Okay, so as I mentioned, over the last 10 years, and my group has been working on this rare Higgs decay search. And so we have 5 papers on this on the different final state like G gamma, gamma star, and also this gamma. And so let's look at the first one that we had. So this is the one we published in 2013. And you can see that around 125 GB, and the limit was about 10. So it's, wow, 10. It's far away from 1, right? So it's at that time, we didn't have very good sensitivity for this search, okay? But anyway, we use the data, and then we build up our analysis technique at that time. And then we also look at gamma star gamma. Actually, when we proposed to work on the gamma star gamma, my CMS colleague mentioned that this is an interesting one. But it turns out actually at 125, you can see the limit at that time is what at 6. So this has much better search sensitivity than the G gamma. And then in the 2018, that we published another paper with more data collected at certain TV. Then you can see actually the limit was for G gamma, it was decreased from about 10 to about 5. Okay. And so namely the search sensitivity was improved doubly. And then for the gamma star gamma, this reduced from 5 to about 2. Okay, so of course, we use this new data we collected at OC, and then this is the analysis strategy in our analysis. So first of all, we have the event selection. This is mainly try to clear the background. And then we have some reconstruction, like, well, in our jargon, we call this final state radiation recovery and kinematic refit. So these 2 steps are very important to improve the mass resolution of our signal. And then we have the categorization and to improve our search sensitivity a bit further. And then we try to model our background from the data. And then we perform the analysis, we extract the result, okay? And so there are many technical details, but I'm not going to talk about it today, but I will directly show you our newest result of the Higgs-2G gamma search with the full round-2 data set, namely 138 inverse femtobound data from the CMS. So here you can see that around 125 from the lab plot, that you can see around 125 GB. It's quite interesting that after about 10 years, that we start to see there seems to be a quite significant bump around 125 GeV. Okay, so we try to measure its signal strength. So its signal strength is quite large. It's about 2.4. Of course, the uncertainties is quite large at this moment. In particular, the statistical uncertainties still dominate at this moment. We also measure its production cross-section, so it's consistent with standard model prediction at 1.6 sigma level. And so since we have we observe bump layer, so we try to set the significance under the background only hypothesis. So we actually, according to the standard model, what we expect was 1.2 sigma with the given amount of data we have, but what we observe is 2.7 sigma. Okay. And then at the same time, in CMS, we also try to measure the ratio of the branching ratio of Higgs to G gamma to the branching ratio of Higgs to gamma gamma. And because this number actually can be sensitive to the beyond standard model. And so the standard model prediction was 0.7, and what we measure is about 1.5. So this agree with the standard model at 1.5 sigma level. Okay, so this is the news result that we have. And how about the result from another experiment at the CMS, at the LC? There's an Atlas experiment. It's quite interesting is that actually between CMS and Atlas, the theoretical inputs are similar, and the expected sensitivity is similar. We expect 1.2 sigma. They also expect 1.2 sigma. And if you compare the measure results, actually they are quite compatible. We observed 2.7 sigma, and Atlas observed 2.2 sigma at 125 GB. Okay, and the mass resolution is also comparable. We have 3.7 GB. They have about 4 GB. So this is quite interesting that two experiments have the same expected sensitivity, and then it seems that both experiments observe a bit larger access from the data, and of course, yeah. So this is quite interesting, and then this we will continue with this search with the data we have in the round 3, because round 3 will start soon next month. So in the round 3, we will increase the collision energy from 13 to 13.6 TeV, and we expect to collect about 250 inverse femtobarn data in the next 4 years. And then we will have a long shutdown 3 for the phase 2 upgrade. And then the high remaster LC, then we will collect protons at 14 TeV, and we expect to collect 250 inverse femtobarn data per year. And then so by 2045, then actually we expect to collect about 3,000 inverse femtobarn data. And so far we only collect about 5% of data. Okay, so yeah, so we expect more data to come, and then yeah, so we will continue to look into this rare history decay, and let's see how we get with more data. Okay, so then I will switch to another topic, that is the muon graph that we have in at NCU. Well, after working in this kind of large collaboration for 20 years, sometimes you can be tired because sometimes you don't have freedom to work on the thing you want to work on. So so we start a standalone experiment in NCU. And so this is a muon graph. I will start with a bit history about this. What is it? So actually, in about 1950s, the Eric George, he first used the muon graph to measure the depth of the rock about a tunnel in Australia. And then about 10 years later, Nobel Prize that he tried to use this muon graph and to explore the internal structure of a pyramid in Egypt. Okay, and actually it's quite known. And however, actually, due to the detector technology, actually, this technique was not very popular, although it was started in 1950. However, recently, due to the improvement of detector technique, so actually recently, you can find actually the number of publications on the muon graph has been increasing. Okay, and so for example, in the 2003, the physicists in Los Alamos, they developed a scanner to find a block of uranium inside, concealed inside a truck full of ship. Okay, and in addition, the European countries and Japan, actually they use this technology to monitor the volcanic activities. And for example, in the middle, this is a density map from a Japanese earth scientist, and they use this technique to monitor this volcano. And for example, another thing is that in Fukushima nuclear disaster, and they also use this technique to measure the amount of radiation and explore its distribution of the nuclear reactor. Okay, and so the muon, actually, this was found by Carl Anderson in the cloud chamber. and then its mass is about 210 times heavier than electrons. And that's why this makes it unique comparing to electron. And its muon lifetime is about 2.2 times 10 to minus 6 second, sorry. Yeah, second. And then the muon, for example, the muon with 1 GeV, it can penetrate 1 meter of the ion, okay? And so actually the muon has a very good penetration power. So yeah, so that's why it's good. And it can be used to explore this kind of giant object like mountain or volcano. And so actually the muon usually we detect, we call it a secondary Casimir ray, because the primary Casimir ray mostly originate from outside the solar system and sometimes even the Milky Way. And so actually the primary for the primary Casimir rate, it's 90% is about protons and the 9% alpha particle and about 1% electron. So for example, when the proton coming into the Earth, so the proton will interact with the molecules in the atmosphere, okay, and then will produce the particles like a pion or like a nucleon, and then the pion will immediately decay into the muons in 10 to minus 8 seconds. Okay, so then because the muon has this larger lifetime, so that they can arrive at a sea level. And then, so actually, the left photo that shows you the muon, where the muon comes. Actually, the muon come from everywhere. This is the photo from a spark chamber. So you can see actually the muon come from everywhere. So muon actually is the richest charged particles at the ground level, and the average energy is about 4 GeV. And the muon flux is about 1 muon per centimeter square per minute. And in addition, actually, muon has actually the muon flux is not really well. I mean, in terms of the zenith angle, the incident angle, muon is not really uniform. Actually, from the bottom plot here, you can see actually the muon flux actually it changes as a function of the incident angle. Okay, so you get more muon flux from the top of your head, and then you get much less muon flux at the incident horizontally. Okay, and how about the principle of a muon graph? Actually, well, it's easy. Like for example, if we have a study target like a mountain, and so when the muon coming in, and then we will install the detector on the other side of our study target, and then so from this, in our detector, we measure the amount of muon flux, okay? And then from this measure the muon flux, and then we perform an inversion, and then what we want to get is a density map of the target we would like to study. So that's the basic idea of a muon graph. So actually, in my group, we spent about 2 years and to develop this muon detector. We developed several prototypes, and in the end, this is our final product. Okay, so in this one module, and we have 4x4 scintillators, and then the signal is read out by this SIPM, and then transferred to computer by the FPGA. Okay. And so we performed the first muon graph experiment in front of this tunnel called the Amupin distilling tunnel in the Siemens Reservoir. And so here you can see that in front of this tunnel, we built a wooden bridge. And actually, working on this experiment is quite interesting. Is that well, you need to start from scratch, and then actually there is no power there. So you can see there were many batteries on the bridge, and actually we need to went there every 5 days to replace the battery in order to keep our detector running. And then so we run the detector there for almost 7 months to collect the data. Okay, and on the right you can see this is how our first detector looked like. So we have 4 layers, and each layer has just one module. Okay. So this is the work in progress result from our measurement there. So here, what I show you here is the muon flux measured when our detector faces the mountain, divided by the muon flux measured when the detector faces free sky. Okay. So if you have a larger value here, it means that the region, this pixel region you detect, actually you have less material in front of you. Okay. So far, since we have only one detection location, so we can only detect this map in 2-dimensional. However, from our first work in progress result, and it's quite at least it's quite encouraging to us, is that it seems that we already in this pattern, it seems that we have seen the boundary between the free sky and also the mountain, the top, the surface of the mountain. Okay. So right now we are still performing a very detailed analysis on the result we have. So this is still ongoing. And so right now, of course, our first detector is quite small. It's just 4x4 scintillator. So the size is about 20 times 20 centimeters square. And of course, in Japan, for example, right now the detector they use in the muon graph is 2 times 2 meters square. It's quite large. And so, of course, we would like to build a larger and larger detector. So right now, the second generation muon detector we are trying to construct in NCU is that it's going to be a 40 times 40 centimeter square. So we are working on it. It's about to finish. So yeah, so we will install it soon. So that's our plan. And so in this Amupin region, actually, on top of this tunnel, actually there is a Xindian fault, Xindian 断层. So my collaborator from the Earth Science department is quite interested in knowing the density map of this Xindian fault. Actually, they know a little bit about it, but they want to have a very complete picture about this fault, about this tunnel. So in 2021, we finished the measurement at the D1. Okay, and this black straight line shows you this tunnel actually is in bottom of this region. So in summer, we plan to install our first and second detector in these two sites, D2, and there's a temple at the region. So we already talked to the people in this temple, and they will offer us a space to install our detector there. So we were in this year we will perform the measurement in these two additional locations. So therefore, if we can have the measurement from these 3 different sites, then we will be able to perform a 3D. We will be able to obtain the 3D density map for this region. That's our plan, and of course we have more plans. Like in the future we would like to install our detector in the Datunshan and also the Jingguashi, and try to study a few geophysical issues there. Okay, so this brings me to the summary. So far we collect about 5% of data at LHC in the past 10 years. And the Higgs boson was discovered on July 4th in 2012. So far, the physics property of the Higgs boson agree with the standard model expectation. We haven't found other new physics at LHC yet. However, the discovery of the Higgs boson opens a new window for us to explore the new physics. And to me, actually, I think it's a very good timing for the new student to join the LHC experiment, because we will have a phase 2 upgrade in 2028. So the new detectors actually are being built, and so it's a good timing and to get your hand dirty and know and learn how the detector is built. And in addition, that we will continue collecting the data, so a significant amount of data will come soon. And apart from participation to the large international experiment, and we started to develop the application of particle physics, and that is the muon graph in Taiwan. And yeah, we hope that we can be a larger detector and more detectors, and then we can use them to explore a few geophysical, to study a few geophysical issues in Taiwan. Yeah, and of course, the result I have shown you so far, actually, it all come from the work of my students. Without them, I mean, I cannot show this result. Okay, yeah, thank you, thanks. And so that's all I have for today.
Okay, great. Thank you.
Okay, great. Thank you.
Should I mute?
Yeah, maybe. Yeah, thanks.
Okay.
Right. So I think it's very, very interesting. About the things that we've been doing and trying independently at National Central University, because the majority of the audience today is actually from our master program. So perhaps the students here could consider doing PhD at the National Central University if they want to work on things like the myography technology, detecting the things related to the geoscience. And certainly they can stay on over here to work on the LHC through the collaboration between the NCU, NTU, and other institutions. So now I'm going to open the floor for questions. So any questions from the meeting room and also from the webinar room?
This is Chen Wei. Can I ask questions?
Yes, go ahead, please.
Great. Johnny, thanks for the nice talk. I have actually two questions, one for each part. Probably because I had some connection problems, so I missed your explanation. But you explained that in the Higgs decay to gamma-gamma star and then decay into electron pair or muon pair. The electron pair has a larger branching ratio than the muon branching ratio. I want to ask, why is that? I missed the explanation.
Okay, so yeah, so actually, this is a question that I was often asked by my collaborators in CMS because they cannot figure it out. And okay, actually, it's quite simple. Is that in the gamma star, right? So if you look at the lowest invariant mass of gamma star from the muon pair and the electron pair, if you compute it, actually the electron pair will give you the much smaller gamma star mass comparing to the muon pair.
Okay.
Right. So right. So as we learn in the modern physics, you compute the invariant mass. So let's say, okay, the muon pair is about 2 times the muon mass. The electron pair will give you 2 times the electron pair mass, right?
Yeah, but I'm just wondering, because given the fact that Higgs is so massive,
right. Higgs is so massive, exactly.
Basically massless to the Higgs decay.
No. Actually, the gamma star will carry away the energy. So actually, what I show here actually is what we get from the Monte Carlo. So this is and then also from the theoretical calculation is that this is the lepton invariant mass. Okay, and so here you can see is that I don't know whether you can see it clearly. Okay, so here in the gray histogram, so this is the dielectron before the selection. Okay. And then the pink histogram, this is the dimuon distribution before the selection. So there is no selection involved here. So this is purely from the generator. So you can see, of course, we don't divide it. So you can see actually electron has a much larger contribution at very low mass. Actually, if you go to high and high mass, actually there is no difference between electron and the muon, as you can see in the Higgs 2G gamma prediction. But if you include this small region, okay, below 0.5 GeV, actually the electron has a much larger contribution compared to the muon.
Okay, that part I can understand, but how the question is, how do you select your samples?
What do you mean? How do you? Sorry, what do you mean select? You mean when we perform analysis, how do we select the event or?
Yeah, how do you select the event, or maybe you impose an invariant mass cut on the dilepton so that you remove the low invariant mass?
No, it's opposite actually. In this gamma star gamma analysis, it's object. Actually, here above 50 GeV, we call it Higgs-2G gamma.
Right.
Below 50 GeV, we call it gamma star gamma. So actually, in gamma star gamma, we don't place a lower cut. We put an upper cut below 50 GeV.
Okay.
You see? Okay. Yeah. So in gamma star gamma, we focus below 50 GeV.
Okay. Then
Right.
But anyway, so you're telling me that the difference comes from very low invariant mass region.
Exactly. Yeah.
Can I ask a second question, Pradi?
Yeah, sure. Yeah.
Okay, thanks. So the second question is about this muography experiment. Can you go to like page 49?
Wow. Okay.
Yeah, this so you use these detectors as your, I imagine it's like when you go to the hospital to do the X-ray, they are just like films, right? The X-ray films. So it seems to me that they are pretty small. And how do you measure, or how do you take the picture of this, the whatever, the mountain or the tunnel or whatever?
That's actually related to my
Yeah.
question too. You probably do the scan. Do you actually do the 2D scan? Because you have these
Okay, so here you can see.
detectors, so they have this directional sensitivity. So I suspect that you probably do
Yeah.
some 2D scan there, right?
No. We
No?
just simply We just simply place a detector to face the mountain. Because in this detector, as I mentioned earlier, in this detector in one module, we have 4x4 scintillator. So we have 16 readout channel.
Yeah, 16 pixels.
16 pixels, yes. And then we have 4 layers. So you have different combinations. And my student computer combination, but sorry, I never remember the combinations. So you can have combination from different directions, muon from different directions.
Yes.
Right.
But I'm talking about the resolution, right? We want to know.
Okay. So resolution depends on the distance from between the mountain and our detector. In our first experiment, actually the resolution is about 40 to 50 meter. So here, for 1 pixel, I show you here. Actually, we detect a region of about 50 times 50 meter square. And actually, comparing to the traditional detection technology in Earth science, this is much better than NEM, because usually for NEM, their spatial resolution is something like 1 kilometer.
Oh, really? But how?
If you go it's what I learned from my collaborator.
If you go to page 50, how do you get that kind of information?
Okay. So what kind of information? Okay. So for example, this is the experiment we have last year, right? And we simply place a detector here, and we know the distance for the object we want to measure, right? And then we get this 2D, okay? And then in the future, we will add the detection in D2 and also tempo. So we can combine the measurement from different region, because the detector at the different locations and the different angles, they will try to scan the different region. Actually, I have, sorry, I didn't show it. We have another plot to show you the overlap in 3D. And then, so we can explore the region. So for example, can you see my mouse here?
Yes.
Okay, so for example, if we have detector 1, detector 2, and if we place the detector at a tempo location, and we try to scan this region, then we will be able to detect this region. And we can also move toward this region, and we can explore this region. Yeah.
Okay, I see. Thanks.
Right.
So the key thing is we need to have more detectors and larger detectors, and so that we can perform the measurement quickly. Yeah.
Right. So
otherwise, it really takes.
So it seems that the field of view is decided by the size and also the distance of the parallel panels, right? Because if you put them closer, then field of view will be wider. Otherwise, it will be shorter. So if you add on 2D scan, you can probably increase the field of view. But anyway, Yeah, I have a
Yeah,
question.
but you have to. Yeah, sorry. Yeah, go ahead.
Yeah, okay, thank you. Yeah. So there's a question from the webinar room. It says that it's from Paganis. The question is the split to ZG and to star gamma is not gauge invariant. So the strictly correct four channel description is 2 gamma. Strictly speaking, they cannot be separated, although experimentally we do. So I'm not sure if that's a question
You
or
mean
that's a comment.
theoretical? Yeah, theoretical. But yes, theoretically you cannot do that, but experimentally we don't really have a way, right? I don't know whether Stacy can speak.
No, unfortunately, he's in the webinar room. Actually, yeah, Stacy could actually join the meeting. I'm not sure if he got the address here. Yeah, it's a bit inconvenient.
Okay, maybe I can
Oh,
discuss this
he
with
said
him.
you are correct. Yeah. Yeah. Stasis responded that you are correct.
Okay.
So any more questions, especially from the students?
Hello, Professor Zhang. Hello, can you hear me?
Yes, just go ahead.
I have some question about the muon detector you mentioned.
Professor Guo, you're talking about Professor Guo?
Yeah.
Okay.
Sorry. Yeah, and I'm curious about how long are the muon detector going to take for each spot, because as you mentioned, the muon flux is about one count per square centimeter per minute, and as your detector is 40 square centimeter big, so and the resolution is 256, so which means for each beam the effective rate is only 0.6 count per minute. And however, after the muon just attenuated after passing the mountain, the survival rate become very, very low. So I'm curious about how long are you going to take for each spot?
Okay, yeah, good question. So indeed, I mean, the rate is very low, and another factor that you need to take into account actually is also the incident angle. Here, the muon flux is about 1 muon per centimeter square per minute. Actually, it's coming from top. And as I show you in this slide, actually, if you go to the higher and higher incident angle, we call it zenith angle, that actually the muon flux will decrease as a function of cosine theta square. Okay. So indeed, I mean, in this experiment, in our first experiment, actually, at that time, the angle was at the 5 degree, actually. So the rate was really, really low. So that's why it took us 7 months to collect the data. Yeah. So therefore, actually, yeah, we have a based on the number you mentioned, and also based on this cosine theta square, we can do the calculate. Yeah, we when we perform the experiment, actually we have a calculation. Yeah, yeah. So yeah,
So-
in our first experiment, the rate was really low, indeed.
So may I ask what is the standard deviation you can get after the standard deviation for your myography after you take about 7 months?
Okay. So I don't have. Okay. So for this 7 months for this plot here, so for the largest pixel, that we collect something about 400 to 500 muons
Okay.
from the top. In the bottom is much less because in the bottom we have the mountain, right? That is much thicker in the bottom. So we get less statistics below. But in the top, it's about 400 muons after 7 months of data taking.
But it seems like the mountain is kind of so flat in this myography.
No, it's not flat actually. Sorry, it's not flat. It's not really flat. Sorry, I don't have. We have a no. It's not really flat. From this plot, you can see it's not really flat. It has some
Oh,
structure. You
okay, I
can see.
see.
Can you see my
The
mouse
right
now?
side, upper right side.
Exactly. Exactly. So actually, this is the top of the mountain. Actually, the top of mountain is here,
I
and
see.
then this is the shoulder. This is the shoulder of the mountain. Yeah. Yeah. So actually, now my student is trying to draw the mountain shape on top of this plot. So it's better for visualization.
Okay, thank you.
Okay, any more questions from the audience from both sides? Let me see. There's no question from the webinar room. If not, oh, there's one raising the hand. Yeah, just speak up. Yeah. Yeah, go ahead. The R09222063. You can speak up. We don't hear anything. You probably need to unmute yourself.
Hello.
Yeah, go ahead.
I have a similar question. Will the power of your detector influence your measurement? Because it said you have to change your battery
Why?
every few months. So will that have an impact on your measurement? And since it took a very long time, so I wonder if the results will be influenced by this.
Okay. No. Yeah. No. It will not. Actually. Okay. In this experiment, I mean, actually, this powering system was designed by my students. And actually, when they design this powering system, actually, right, they try to make sure, actually, when we replace the battery, and the detector still have power to operate because we have a switch. We can switch. So actually, the downtime was very limited. And when we analyze the data, when we know there's a downtime, so when we compute the muon flux, actually when you compute the muon flux, there is a term called the number of times you collect the data in the denominator. So we will remove the datetime. So the answer is that no, I mean the datetime will not affect our result.
Thank you. I understand.
Okay, any more questions from the audience? Not from the webinar so far. And from the meeting room, there are two messages here. Oh no, it's not related. Okay. Okay, so if there is no further question, then let's thank Professor Guo again. Yeah. And
Thank you, Tommy.
yeah, it's great talk. Very interesting. Yeah. Very, very interesting. Yeah. So next week, we will have our last talk by Li Luoquan 院士, and yeah, that will be the very last talk of this colloquium series for this semester. And for the guest, for the speaker, and for the faculties, you can leave now, and RTA is going to do the 点名 for those who are actually taking this course. So thank you again. Yeah, 郭嘉明，谢谢。哎。